Well, hello, awesome physics students. So today we are going to talk about Werk. So let's get to it. So in the previous video and in class, we've talked about these energy buckets. We could treat energy like energy juice. Because it's a scalar, we don't need a direction. Okay, so we have these energy buckets. We've also talked about our LOL diagrams where we have the different types of energies in the bar graph, and we have our system right there, and then we have that different types of energies at the end as well. So, but the one thing that is always true with everything that we've done so far is that the energy initial equals the energy final. In this case, in this example with the ball falling, our energies, our total energies, are always 50 joules. The energy could slosh back and forth between the kinetic and the potential energies right here, but our total energy was always constant. So now we're going to look at examples and see how to treat things when the total energy is not constant. Okay, so we have a box moving to the right and on a rough surface. So it looks kind of like sandpapery down here. And as the box moves, it's going to slow down. So the kinetic energy bucket is gets depleted. But our total energy for this, so our total energy bucket gets depleted because the box isn't raising, it isn't going up. And the box, so potential energy doesn't change. So the only thing that changes is kinetic energy, so the total energy must change. So the best way to look at this is through an example. So here we go. We have a 10 kilogram block. 10 kilogram block on wheels. So let's ignore friction for this problem. Is initially traveling at 2 meters per second. A force of 2 newtons pushes the block for 10 meters. How much is the kinetic energy bucket filled in this time? Okay, so if we want to find how much our kinetic energy bucket is filled, we have to know our initial kinetic energy. And then we want to know our final kinetic energy. So if we're going to be pulling it, it's probably going to be speeding up, right? So we're going to have our final kinetic energy. And so then the change in this, so let's erase this and we'll do kinetic energy final, which is more, minus the initial, which is less, equals our change. Okay. So let's see. Well, kinetic energy, if we remember, is equal to 1/2 mv squared. Okay, so if we could solve for the initial, because we're given everything. Kinetic energy initial is equal to 1/2 mv squared. So that's equal to 1/2, the mass is 10, times velocity, which is 2 squared. Okay, so this 2 squared is 4, so that's 40, and 1/2 is 20 joules. Okay, so we know that kinetic energy initial is 20 joules. There we go. All right, so now we need to know kinetic energy final. So kinetic energy final is equal to 1/2 mv squared. We need to solve for this final velocity. Well, let's see. Well, we could go to kinematics. So we have our givens. So A, VI, VF, change in x, change in time. Okay, we are not given A. VI is 2 meters per second. VF is what we want. Change in x, it goes for 10 meters. So now we need one more number here so we could use our kinematic equations. Well, we're given a force, and whenever I think of force, we could solve for acceleration. So let's draw a free body diagram. So we have a free body diagram. We have the weight by the earth on the box. We have the normal by the ground on the box. And we have this force. And since there's no friction, we don't have to worry about this. And so the acceleration is to the right because the net force is to the right. So the sum of our forces equals ma, and that's only going to equal that force that's given. So now the mass is 10 times a equals 2. So a is equal to 0.2 meters per second squared. And that could go up here. Okay, and now we could use a kinematic equation that doesn't involve time. So Vf squared equals Vi squared plus 2a change in x. Okay, so Vf is what we're looking for. Vi is 2 squared plus 2 times 0.2 times 10. So 0.2 times 10 is 2. So it's 2 times 2, which is 4, and this 2 squared is 4. So 4 plus 4, Vf squared is equal to 8. And if you notice over here, we have Vf squared, so we could just put in 8 for that. So it's 1/2, let me change our color back to red, 1/2, the mass is 10, times Vf squared, which is 8. So 1/2 of 8 is 4, times 10 is 40 joules. So our change in kinetic energy, change in kinetic energy is equal to the final, which is 40, minus the initial, which is 20, equals 20 joules. Ta-da! Okay, so this was a very involved problem. We had to look at the kinetic energies first. So first we had to look at the kinetic energies. We had to look at how they changed. And then we found out that we needed this final. And we said, okay, so then where do we go? We went to our givens, and then we found out that we needed one more piece of information. So then we went to our free body diagrams. We drew a free body diagram. We solved for we wrote our F net equation right here. We solved for our acceleration. We went back up here, plugged in the acceleration, solved for our final velocity, and then we went back here and went to the original problem of needing the final velocity. We put that in. We got our final kinetic energy, and then we were finally able to go way back to the beginning and do our final kinetic energy minus our initial kinetic energy equals our change in kinetic energy. And this change is the amount that the box gained. So in this case, the box sped up, so we have more energy. Now you might be thinking, oh dear Lord, Mrs. Bauer, this is a lot of work. Isn't there an easier way? Well, there is. Okay. So let's look at this equation that we had. Vf squared equals Vi squared plus 2a change in x. That's our kinematic equation that we used in this problem. Let's subtract Vi squared. We're going to manipulate this around a little bit, and then you'll see why. So let's subtract Vi squared from both sides. So we have Vs squared minus Vi squared equals, and then so since we subtracted it from this side, it goes away, 2a change in x. Now remember that F equals ma. So I could write a as F divided by m. So we're going to substitute that in right there. So Vf squared minus Vi squared equals 2F divided by m, change in x. So I am going to multiply both sides of the equation by m divided by 2 because I know where I want to go with this. No other reason. So that cancels out that 2, it cancels out this m. And we are given, and I could distribute this, so it's 1/2 mvf squared minus 1/2 mvi squared equals f change in x. Do you see it? Do you see it? This is kinetic energy final, and this is kinetic energy initial. Ooh, so exciting. Okay, so kinetic energy final minus kinetic energy initial, if you remember, that's our change in kinetic energy, that's what we're looking for, is equal to a force times the displacement. So this force times displacement is our change in kinetic energy. The force changes our kinetic energy. The quantity F change in x is called our Werk. Now, if you are going to look this up on the internet and stuff, it's really called Werk. But we use work in our vernacular so much. I'm doing homework, I'm going to go to work, this is a lot of work. But work in physics has a very, very specific, even an equation. It's a very specific meaning. It means change in energy. And so to separate our work, our physics work, and I'm not even talking about our physics like homework or doing work, but our physics definition of work from our vernacular, we'll sound like smart Einsteins and just call it Werk. So that's why we write it this way in this class. So that's our Werk. So what are the units for Werk? Well, the units for energy is a joule. So we have a joule minus a joule better give us joules. So what's the units of energy? It's a joule. Okay, so let's go back to our example. Let's revisit that example, that hairy example. So we saw the 10 kilogram block on wheels is initially traveling at 2 meters per second, and a force of 2 newtons pushes the block for 10 meters. How much is the kinetic energy bucket filled? Well, we know that the Werk is equal to the change in kinetic energy. So it's just this force times the distance traveled equals our change in kinetic energy. That's it. This one line equals all the work that we did in the previous page. Can you believe it? Isn't that awesome? So cool. Okay. Now, I must say, and this will come up in the example problem in the next video, this force and change in x must be in the same direction. It must be in the same direction. And we'll explain why in the next video. Okay, so how does kinetic energy change? So if F and change in x are in the same direction, the kinetic energy is going to increase because they're going to speed up. Oops, and this should be change. I forgot to fix that. So this is change. That's our change symbol right there. Change in kinetic energy is positive. Now, if the force is going backwards, so if the force, that outside force is going this way, but you're traveling this way, so this bubbles is going this way, but let me do it the same. If this bubble's going this way, but I'm pushing it this way, it's going to slow down. So if it's going to slow down, the kinetic energy is going to go down. And so our energy bucket, the energy in our energy bucket is going to decrease.